Okay, discussion time. Wow, this one had some real easy types of observations that prompt you to discuss some things here. So that's the reaction. So right off the bat, we want to talk about percent yield and some of the things that we were looking at. We definitely see some black color, so right away we start thinking, sometimes when we see that, it's very indicative of decomposition, which leads us to thinking, is this typical of a Jones oxidation? So yet again here, folks, we've had some observations that are leading us to think about that, okay? So then from there we say, okay, we're still in the thing of percent yield. We'll come back to the decomposition. So part of percent yield, and not just the decomposition issue, is this compound has a large solubility in water. And that's part of the physical constants that you had. And we also notice it has some volatility too. Sometimes when you're running this on the salt plates, if it's too concentrated, you take the two salt plates apart. It was very easy to see that if you even ran the IR right away and it was still too concentrated, when the two plates are apart, you could see how like 2 minutes later you rerun the IR, and obviously a lot of that stuff had evaporated away because the IR was a lot less concentrated. So a couple of big issues here. Large solubility in water, which, by the way, I didn't believe it myself. I actually put some in a test tube with water, shook it up, and surprisingly, cyclohexanone does go into water. It is volatile. So then with this in mind, we're thinking, okay, the volatility, okay, we're rotovapping, one thing that we're going to lose quite a bit there. And then why are we washing the ether layers with, at the very end, 2 more water layers? So you reread the procedure, clear as day. Once you get your combined ether layers, you wash it with sodium bisulfite and then 2 water washings. So that seems like we're losing a lot there. So the classic way of settling this, if you're thinking like a process chemist and you have to offer proof, liquid chromatography is the way to go. So in this particular example, ideally, what would be your samples for liquid chromatography, where you're looking for organic material? Where is all the organic material? Even the acetone too, which, by the way, was part of the Jones reagent. So anyway, the original aqueous layer, you could have that layer sitting there on the bench. You're going to have the sodium bisulfite layer, and yes, folks, I'm questioning that because from my memory's terrible. I don't know what that is. Is it page 11 in the nomenclature book from first year or something like that? Sodium bisulfite, is it SO3, SO4, SO2? And you can look that up. So you got one of those layers, which could have cyclohexanone in it as well. Then you have your last 2 water layers. So in an industrial process, they would want you to run a sample of each of these and find out exactly how much potential starting materials in there, or product, or any other signs of things that could show up that are organic, right? And then of course, they would also want you to run your ether layer before rotovapping, so you could actually get a better quantity of what's in here. And then if we wanted to settle the decomposition question, is it typical of Jones? With something as our compound, which is so volatile, why don't we pick an organic compound that has very little volatility? You could attach on a benzene ring and see how you still have a cyclohexanone system, but it's a lot heavier. This compound, just as an example, you could test it under Jones, and then you could carefully do the same type of liquid chromatography analysis, but you won't be losing any to volatility. So you'll be able to find all the organic material, and then your percent yield, once you've accounted for all the organic material, anything missing would likely be gone to decomposition. So you could settle that question there. So folks, this page is all about surrounding the ultimate sort of percent yield. We're trying to make and prepare that compound. We have questions of decomposition. We have solubility, volatility issues. How do we go about processing our workup? We want to analyze it. That's what would have to be done to find out answers to those questions. You also have the issue of most students have diethyl ether and acetone in their NMR. So clearly an NMR ratio could be done through moles first, then mass, to correct your yield, to account for the mass of the diethyl ether and acetone that your NMR clearly shows. Many of you it does. Now, the blue dot. Many students have noticed that before rotovapping is very clear. When they're done rotovapping, they hold it up, look in the light, and they see like a little tiny blue dot on the bottom, like a little tiny bit of aqueous layer or something, but it's blue. Well, the blue color indicates that that little blue dot is going to have some amount of chromium in there. So that leads immediately to a question, not unlike, remember in first year organic with Barry, mercury, you did a oxymercuration, and a lot of students found that even though before rotovapping they had something clear, when they're done rotovapping they see little tiny droplets of mercury. So clearly the intermediate in the oxymercuration was stable enough to last that long before falling apart, liberating the mercury, and that was before. Now you have a similar thing where the question is, somewhere in the mechanism, you see an alcohol attack this, and many books do it different ways, but you get something that they're going to call, what is it, a chromate ester or something like that, an intermediate that arguably, if this observation is true, that intermediate of the chromate ester could be stable enough that it does take some time to eventually fall apart, liberating the chromium in your product. Now that's a possibility. Okay, now that's something that obviously further studies and tests could be done to confirm it, but it's definitely a plausible thing. The other thing that corroborates this is the NMR. I ran a few already this year and last year, and one of the NMRs I ran this year, I noticed that they had very, very sharp, and this is called line broadening in NMRs, okay? If you have any chromium-6, that's a paramagnetic thing. It has unpaired electrons in the atom itself, and that causes line broadening in NMR. So if you ran a sample, and let's just pretend it was, you had some diethyl ether, you're looking at the quartet. If you had no chromium in your sample, you get very nice sharp quartet of diethyl ether. But if you got chrom-6 present, a little more or less, you see this kind of ugly looking quartet. And that's how we used to say, oh no, we're pretty sure we've got some paramagnetic chromium in there is what we'd say. So a lot of times we would actually go back and we'd filter our NMR sample through C-Light and we'd rerun it. So going back to this, even the NMR, one of the students whose NMR this year was very sharp, they never noticed this blue dot. Whereas many of the others, when I ran them already, it looks like this, and they did comment when they're done, they noticed the blue dot, indicating chromium being present, which leads us back to the possibility of that chromate ester. Okay, so I mean that's an interesting thing to look at. One of the other main things you can talk about is color changes, just like the previous lab where you had sodium dichromate or something like that. Obviously, somewhere in this procedure, you start out with chromium mixed with acid, very orange, right? You're going to have chromium in very different environments, different solvation solvents, different oxidation states of chromium as it goes through its mechanism. So as we added some of this, many people are going to report different colors that they've seen, and this is all tied to the fact in crystal field theory, and we already talked about that last time. These are the 5d orbitals. Any metal that's not totally by itself. As soon as it could be something as simple as water molecules coordinating to it. It'll cause two of the d orbitals and 3 of the others to split apart, and it's usually in the visible part of the spectrum, and that's why it absorbs part of the visible spectrum, and you see what's left over, and that's how you get it. So the extent of that splitting depends on what is solvating around in what oxidation state. The other thing that we could comment on here, another observation. Most people, after they did some addition right at the start, and then they let the solution sit for a minute stirring, it becomes clearer, still blue or teal or something like that, but then they notice there's some black either solid or a goo that was swirling around on the bottom of the flask. So that's another interesting thing that leads you to wonder, okay, what exactly is that stuff? So one of the things that could be done, if we wanted to find out what it is we could redo the reaction and right at that stage, because a lot of that black chunky stuff, or goo, by the end of your processing of washing it with sodium bisulfite and the rest, goes away, doesn't it? So the question is, what is it in the meantime? So arguably maybe we could filter it at that time, take a look, see what it is, but it's also interesting to see that that stuff does go away. If it didn't, it'd be clogging your separatory funnel, right? So folks, this, and again, the one thing I wanted to point out, and I must also make, when you go to write this, when you come up with almost like a little paragraph that you envision writing, ideally, if the front end of the paragraph has some indication of observations forcing you to either discuss or explain. You can, if you want, put a little bit of sort of theoretical comments in the meantime in the paragraph. So start off with kind of the observations or results that have forced you to start discussing what you're going to have in this paragraph. You can add a little bit of theory if you want. That's fine. But then you always want to finish with your sort of discussion, explanation, or comments, right? So I'm just looking at this, going back to the blue dot example paragraph. I mean, obviously you want to make a comment, and if you've seen this blue dot, so you're bringing up, a blue dot was observed, which is indicative of chromium being there. So you're starting off with an observation. You can even tie in at the same time saying that even the NMR while running it seemed to indicate paramagnetic chromium being present. And then your discussion part of the paragraph, the mechanism, if you take it straight out of a book, that's almost as if in this paragraph, that's your theory. It's not like you are coming up with the mechanism. You just take that out of a book. But you're using the mechanism to point out one of the intermediates, and back to the diagram, that you are now explaining is best to talk about if this intermediate's stable enough, it survived rotovapping for a bit, and then it fell apart. So you can see how in a discussion, you want to always try to start whatever you want to talk about in one paragraph, and you try to stay away from mixing multiple ideas in one paragraph. Make a new paragraph. Try to indicate the observation or result that's forcing you to talk about what you are, okay? But make sure you finish off this sort of paragraph with words that it's obvious come from you and your understanding. Now, last but not least, folks, 1 mark out of 6 is absolutely, I mean, we can sit here and we as a group could discuss all of this. And a lot of us, you all nod our head, it all makes sense. And then we say, okay, now I actually have to write this in as short form as possible. That in itself is not really chemistry. Obviously, we used to have something called scientific writing. So, folks, that's how the whole discussion thing kind of works. You start out having a big discussion amongst yourself, flesh it out, and then you say, okay, how am I going to put this in paragraph 1?